is just putting one braid on top of another braid, right? And the inverse braid, I mean, the braids are considered up to smooth isotopy. So after up to, I mean, we move these arcs so that they keep going downwards, and they don't cross each other. So if you consider braids up to isotopy, then up to this kind of isotopy, then they form a group, and the inverse is the same braid turned upside down, and the unit element is just the braid with all the strands vertical. So this is the usual pure braid group, and nobody here has done more about it than Fred. It's a great pleasure to have Fred here, and I mean it's a bit scary to talk about braids in front of Fred, but I mean knowing Fred, it's not so scary. So this is the pure braid group. It's a very interesting group. There are many things that can be said about braids, and one of the reasons why they're important is that if you take a braid, you can obtain a knot out of the braid, and you can study knots as closures of braids. So somehow you can reduce certain questions about knots to certain questions about braids. It doesn't always help, but it sort of helps to understand some things. So, but I mean, I'm assuming that most of the people know what the braid group is and what it is, what the whole story is about. So there are some generalizations of braids, groups that look like the braid group. So this is there is the pure braid group, and there is the braid group, the full braid group, which consists of braids like this. It surjects onto the symmetric group on n letters. So what we have, I mean, if we put the numbers here, then just following the strands of the braid, you get a permutation. So this is a homomorphism. So we have a homomorphism from the braid group Bn to the symmetric group, and the kernel is exactly the pure braid group. So the pure braid group consists of the braids that kind of start, each strand goes back to where it started, so, sort of. So there are many generalizations of these pictures. There are all sorts of other funny braids, like virtual braids or welded braids or whatever. And I'm going to talk about two generalizations of the braids. Well, two analogs, not generalizations. They don't generalize. They're something similar to braids, and which are of some interest in some other situations. And in part, it's work in progress. But again, I mean, since it's an improvised talk, I mean, it's a disclaimer. I take no responsibility about anything. No, it's not true. I mean, it's all. I'm not going to tell too many lies. So, like there is a kind of there is a story which is parallel in a way to the story of knot theory, and it's the theory of plane curves without triple self-intersections. So, a plane curve without triple self-intersections, well. It's something like this. I mean, you draw a curve, and when you have the self-intersections, they're only transversal crossings. And what we allow on these curves, we allow two kinds of moves, which are similar to the Reidemeister moves for knots. So one move is this. I mean, you take something like this, and this is equivalent to this. This is one move, and the other move is something like the second Reidemeister move. This is the same thing as as this. So we can pull two things apart here. But we have no analog of the third Rademeister move. So we consider plane curves modulo these sort of moves, and the question is what about the classification of these curves? And this question was voiced by Arnold in the 90s, and it didn't really have much application. I mean, the idea, what happened in the 90s was that people were studying Vassiliev invariants. And the general machinery of the Vassiliev invariants, it's applicable to lots of situations. So Vassiliev said, well, I'm not interested. Once I asked Vassiliev something about knots, he said, oh, I'm not interested in knots. And the idea is that, the thing is that the machinery of simplicial resolutions of discriminants, which is something that Vassiliev did, it's applicable to many situations. And somehow it applied to knots and gave a lot of invariance and all that. But there was this kind of, I wouldn't call it industry, because it was kind of, it was not a capitalist enterprise. It was kind of, I mean, people were trying to understand how the same machinery of Vassiliev's simplicial resolutions works for things other than knots, so that we could understand maybe what in the Vassiliev invariance is specific for knots and what is just an artifact of the method, right? So there are Vassiliev invariants for all sorts of objects, and in particular for this kind of plane curves without triple self-intersections. And it turned out, I mean, there are some papers that were proved by, well, Merkov proved that Vassiliev invariants of these kinds of objects really are very powerful in the sense that they can distinguish different non-equivalent curves, can be distinguished by Vassiliev invariants. And this question is still open for knots. Well, to tell the truth, it's not kind of, I mean, so this kind of looks like knot theory, but without the interesting part. The interesting part of knot theory is the third Rademeister move. It's like in this, I'm about to tell the Russian joke, I'm going to laugh. So there is this joke about the Christmas market. So there's an announcement in the Christmas market: dear customers, beware, never buy fake Christmas tree ornaments. They look exactly the same, but they give you no joy. So, so this kind of things, I mean, it looks quite like knot theory, but it kind of gives you no joy. Why? Because you see, the interesting part about knots is that you don't have a normal form for a knot. It's a big problem. I mean, you have a knot, but you cannot say that some specific projection is the normal form of a knot. You can say that it has a minimal number of self-intersections, which is kind of good enough for knot theorists. But there are examples of knots that with a given minimal number of crossings, and you have two knot diagrams with a minimal number of crossings, but in order to move from one knot diagram to another knot diagram, you have to increase the number of crossings. And this is the difficulty of knot theory. I mean, if you try to do knot theory kind of naively and combinatorially, this is the problem. And actually, I mean, distinguishing two non-equivalent knots is, well, it's quite hard. I mean, we don't have a good method of doing it. So, for instance, until like the 60s, I guess, there was this pair of knots in the classical knot tables. For 50 years you had knots. In knot tables you had two knots which were kind of supposed to be different, but then they turned out to be actually equivalent. And this is something called the Perko pair. And Perko was doing his PhD, and he was basically evaluating all known invariants on the knot tables, and he found that there were two knots with exactly the same invariants. So something told him, well, just try and show that they're equivalent, and it turned out that they were the same knot. So this was, unfortunately, since I didn't prepare this talk, so you can check the Perko pair later. Kenneth Perko. So I actually, I have to tell this story. It doesn't really have to do anything, but with Perko. At some point, I co-authored a book on Vasiliev knot invariants, and all the co-authors, all of us were Russians. So we kind of, we speak English, but with some mistakes. So of course it was not me, it was my co-author. And so he wanted to mention some notation. Perko, when he found out that something was wrong in the classification, he invented his own notation for knots, but it didn't really quite survive the time. It became obsolete. So he wanted to mention the obsolete notation of Perko. He didn't want to say it was obsolete. He just wanted to say that the notation was old. But instead of writing in Perko's old notation, he wrote in old Perko's notation. And nobody noticed that. The proofreaders never noticed anything. But when the book got published, and one is curious if somebody reads it. So the first review on Amazon, not quite happy about old Perko's notation. 4 stars out of 5. Kenneth Perko. So, I have to say that he was not happy, but it was true, right? He was not a young man. But whatever. So at least I kind of try to apologize to Perko by mentioning his achievements as much as possible. All right, so this is a big problem. Distinguishing knots is a big problem. And distinguishing these curves is really easy. Because you see these, in these movements, this one is kind of more complicated than this one, and this one is more complicated than this one. It has more intersection points. So you can always, there is a well-defined notion of a simplification of a diagram. If you can apply this move, you simplify it. If you can apply this move, you simplify it. And it turns out that these simplification moves, they basically commute. So if there is a path from one curve to another curve, then you can, just changing it a little bit, you can just show that well, say if there are two diagrams with the same number of self-intersections, then you can move from one diagram to the other diagram, really, well, not quite keeping the same number of self-intersections, but just kind of complicating things and reducing them just one by one, just like this. So in particular, there's also a normal form for such a diagram. So if you want to distinguish two plane curves without triple self-intersections, well, you just bring them to the normal form and compare the normal forms. So this is kind of, so this whole theory is kind of not very interesting. On the other hand, these things really look like knots. So many people actually did something in this direction. So what I'm going to talk about is not really the diagrams, but the corresponding kind of braids. So what are the planar braids? I'll call them planar braids. So what is a planar braid? So we have, the usual braids, they kind of live in this space. And these ones are flat. These ones are flat. So you have two lines. Well, I don't know where. So you have two parallel lines in the plane. You have n points here and n points directly below. And we have several segments, several arcs that connect the upper points to the lower points. And we don't want these arcs to have triple intersection points. And we consider these braids up to, these kind of braids, up to continuous deformations and the Rademeister moves. Well, there are not too many Rademeister moves, things like that. So this is the same as this. So actually this kind of braid group, I mean, I'll call it Bn bar. Well, it's easy to write its presentation. So it's generated by something I call sigma 1 to sigma n minus 1. And these sigmas are, so this is so this is I plus 1. This is sigma I, just the intersection like this. And the relations, are what? Sigma I, sigma j is the same thing as sigma j, sigma I, if I minus j is bigger than 1. All right, so basically this relation says that this braid commutes with this braid, so this by this is the same thing as. So there's a word for that sometimes called far commutativity, when the two generators are kind of, when interesting things happen far from each other. So this is the same thing as this thing, for instance. And so we stick these things together, and in both cases we get the same braid, which is this. So, and the other thing is that sigma I square equals to 1. Also, well, this is basically the second Rademeister move. So this is I mean, it's a Coxeter group. I mean, we all know how these groups work. It's not very complicated. I mean, for instance, it's residually nilpotent in contrast to the usual braid group. And of course, we also have the map from these planar braids, right? Sorry, to the symmetric group. The same way. I mean, we just follow the strands, and we have a kernel. Well, this map has a kernel, and this kernel is the planar pure braid group. So the question is, what can you say about this planar pure braid group? So you can say, well, again, you can say several things, but they're not so. But I mean, this group is slightly more interesting than this one in some ways. So for instance, P1 is not very interesting. This is just one strand going down. It's trivial. P2 is also trivial because, well, P2 has two strands, and so any braid on two strands will look something like this. So we just pull two strands apart, and it becomes trivial. Well, P3 Well, it's the integers. And the generator is this braid. So how do you prove it? Well, to prove it, let's, it's really obvious. Why? Once you notice that Pn is, it's the fundamental group of a certain configuration space, which I call Fn3 of the real numbers. This is the so-called no 3 equal manifold of the real line. So it was studied quite extensively by people like Bjorner and Welker and many other people. Really, it's kind of well, it's a complement to a certain number of linear subspaces in Rn. So what is it? So this Fn3R, this is really Rn with coordinates x1 to xn, minus the set, the diagonals xi equals to xj equals to xk, minus this set where I is and j and k are 3 different indices. So we take n real numbers, and 2 of them are allowed to coincide, or, well, there can be a lot of coinciding pairs, but there are no coinciding triples. So this is the fundamental group of this space. And for instance, well, when n is small, we can actually identify this space Fn3R explicitly. So F33, what is it? I mean, it's R3 minus 1 line, like x1 equals to x2 equals to x3. So we take a line out of R3 and we get a circle. And this is the generator of the circle. You just look at it carefully. So P4 bar O is a free group on 7 generators. So how does this work? Well, you have 4 points on R. Now no 3 of them coincide. So you have R4. But then, of course, it doesn't really matter in which part of R, in which part of the real line these points are. So you can assume that you can move them all so that the center, so that the barycenter of the 4 points is at 0. I mean, it's a fibration with it's a trivial vector bundle. So you have R3 minus several lines. And these lines, I mean, it's easy to see that you have 4 lines which pass through the origin, intersect at the same point. So you have R3 minus 4 lines and the fundamental group. So this is a wedge of 7 circles, and the fundamental group is F7. So the interesting case, the first, I mean, it's an interesting question. It's not a well-posed question. What is the first interesting case? Because really, I mean, when you draw this is probably the first interesting case. You draw this braid and it's non-trivial. Wow, how interesting.
But that generator is given by essentially by the braid relation, right?
Which generator? This one.
That braid relation, but which is missing there.
Right. Well, of course. I mean, that's the reason that it works is that you don't have the third Rademeister move, right? I mean, if you had the third Rademeister move, everything would die in this situation. So P5, maybe it's an uninteresting case, but at least it's a difficult one. So P5 bar, well, maybe it's not uninteresting. So it's also a free group on 31 generators. So this was, I mean, there was a paper last year, and it's actually accepted in some journal by some reasonable people who state this as a conjecture. But of course, I mean, they're algebraists. So so what does an algebraist do in this situation? If you have a group like B5, well, Bn bar in this case, and you have a subgroup which is Pn bar, then you have a recipe called the Rademeister-Schreier method. If you have a presentation for the big group, you have a presentation for the subgroup, and this is just some kind of a, well, it's called a method. It's as if it was an algorithm. But unfortunately, this algorithm, I mean, it works, but it gives out some, well, you have a presentation, so how do you know that this presentation is the good one, right? I mean, you can present something completely trivial in some horrible ways, right? So if you try to run the Rademeister-Schreier method for P5, well, you get conjectures, you get nice conjectures. So this was a conjecture. I mean, there are many ways to prove this conjecture. And one of these ways, I mean, I'm not quite sure how it goes, but the point is that the homology of these spaces, the cohomology of these spaces is well known. So, well, I mean, the cohomology, you see that you only have some cohomology in degree 1, so it kind of looks like a free group, right? So you can just say a few more words and that gives you a proof. Now, for some people, using cohomology is really high tech, and you don't really need it to prove this. So P5, what happens with P5? You have R5, you have 5 points in R, so you can center them at 0, but you can also rescale them so that the sum of squares equals to 1. So you're back to something three-dimensional, which is really S3. So in S3, you have a configuration of curves, and all you have to do is to draw carefully these curves. And this is something you can do. So it will look more or less, I mean, of course, I won't draw the whole S3. This configuration is symmetric. So I will draw 1/2 of this configuration. And this configuration is you take, is like this. You take two tetrahedra, you put one on top of another. Not very good at drawing tetrahedra. Or something like this. And you join these two. You join these two vertices. And so you take this configuration and you extend all these lines. So you have something here. And you have something here. And you have something here, and you have something here. Well, something like this. So you want to calculate the complement, you want to identify the complement to this thing, and it's not very difficult. Because, well, if you can push these tails far to infinity. Well, maybe not far to infinity, but somewhere here. And then you contract some of these edges. So really, you can get the wedge of 31 circles by contracting these things one by one. I mean, it's a kind of an exercise that students do in the first topology course. It's not a trivial exercise, but it's not particularly difficult. So you can actually see these 31 circles. So the question is, what is P6? And this is something that we figured out. So P6 bar theorem, I'll write the word theorem. Because it was a really somewhat a pain in the neck to prove it. So it's myself and Christopher. So the theorem is that P6 bar is the free product of F71, so we have a free group on 71 generators, and well, this is a Z plus Z really. I mean, so it's a free product of 71 cyclic, infinite cyclic groups and 10 copies of the free abelian group on two generators. So this looks kind of complicated, but really it isn't. I mean, you can understand this result. I mean, of course, to tell the truth, how we got this result, well, Christopher just took the computer and got this presentation, and for a while we thought, well, this is horrible, and then I kind of meditated on it, and then we figured out that it was this. But, I mean, it can be really explained easily. So in P6 bar, you have a couple of, you have two elements that obviously commute. And these are, this is this one, and this one. Oh well. So these two things obviously commute because one lives here and one lives there, and of course they commute. And since they commute, you can conjugate them by the same element and they will still, I mean, whatever you obtain will still commute. So